So, towards the end of the last lecture, I was telling you about the speech analysis and synthesis requirements. So, as we had seen in the last class, that essentially we can have a source filter model for the I mean for the speech generation process, and in that source filter model we can say that the source excitation is actually provided by the glottal pulses, and then the vocal tract that acts as a linear but time varying filter. Okay. So, I mean in accordance with the speech requirements, we change the parameters of that filter, okay, so that different sounds as we desire can be produced. So, when we would like to have a speech synthesis, okay, what we need to have is to go in for a speech analysis and synthesis system, which would look something like this, that I mean the one that I am going to describe is called as the channel vocoder, and this was actually developed by Homer in 1980. Okay. And in the channel vocoder, essentially what we are going to have is that there will be a pre-emphasis filter, some pre-filtering basically, and then the pre-emphasis outputs will be fed to a bank of band pass filters. So, here we have the high frequency, and progressively the lower and lower frequency band pass filters will be used. So, it is a bank of BPFs. So, this is the highest frequency BPF, okay, and here we have the next higher frequency or next lower frequency to that, then the next band of BPF, and finally, the lowest frequency BPF, or rather in other words that will be a low pass filter. So, it is a bank of band pass filters that we are talking of over here. So, this is the lowest frequency, and then these filter outputs actually will be fed to rectifiers. Essentially what we want to do is to extract the energy of the different bands. So, given the speech input which is fed over here, we are going to analyze it into different frequency components. So, in the range of 0 to 3.4 kilohertz, we will be having a bank of such filters, and individually every filter bank will I mean every filter bank's energy will be computed. So, what we have to do is that till now everything is analog, okay, but after the rectifier what we have to do is to use a smoothening filter and then A to D converter. So, I am writing here as filter plus A to D converter, and that we have to do for all these channels. So, typically we can show that here, I mean in Holmer's implementation, we have actually 19 such channels. So, we can number the channels like this. So, all these are the different filter plus A to D, and here this is channel number we start from here, from the lowest frequency. So, this is channel number 1 and so on, and the highest frequency will be channel number 19, and the one that is next to it is channel number 18, the one next to that is channel number 17, and so on, and the lowest frequency is channel number 1. Now, this essentially I mean analyzes the speech signal into different filter banks, and along with that we also have the extraction of pitch information, because as I told you in the last class that pitch forms an essential parameter in order to analyze speech, and obviously if it is needed for analysis, it is needed for the synthesis also. So, the pitch information has to be derived from the given speech signal. So, there is an excitation analysis block. In fact, pitch extraction process is quite standardized, and I mean one of the very popular techniques that can be adopted for the pitch extraction is autocorrelation based method. I am not going to describe that over here, and what I would suggest all of you to do is to refer to any of the standard books which I mentioned in the first lecture. So, you can find some good references whereby you can learn about the pitch extraction process, where as I told just now that autocorrelation based method is one of the very effective and popular means. So, at the end pitch will be extracted out of this, and not only that, the excitation analysis block is also going to find out whether the speech signal that is present over here is a voiced speech or an unvoiced speech. So, what we are going to do is to have that decision available from this excitation analysis block, rather the voiced and unvoiced. So, it is a binary decision that either it is voiced or it is unvoiced, and accordingly all this information, okay, that means to say this 19 different filter bank outputs and this voiced unvoiced flag, everything together will be actually fed to the encoder. I mean in fact, there will be a proper bit allocation and everything for all these items, that is to say the 19 channels, then the pitch information also is to be represented, and the voiced unvoiced which is a 1 bit flag, that also has to be encoded. So, together I mean I will just show it in a separate page, that where we have channel number 1 to channel number 19. So, this is channel number 19, the highest frequency, channel 18 and so on up to channel 2, channel 1 being the lowest frequency, and then we have the pitch information, and then the binary decision, that is whether it is voiced speech or unvoiced. So, all this will get encoded. Okay. So, there will be an encoder which will be encoding this information together. So, channel 1 to channel 19 we essentially have its I mean in the process of rectification, what we have done is that we have extracted its amplitude, okay, because signals are bipolar in nature. So, that is why it will be I mean varying to the positive as well as to the negative. So, what we do in the process of the rectification is to extract the envelope of that, and this in turn gives us an idea about that which filter bank contributes to what proportion of the signal. In other words, it is a kind of a spectral analysis that we have done using this bank of filters. And then this encoder's job will be, see, basically here everything is digital in nature. So, all this digital information will be encoded and the appropriate bit stream will have to be generated. So, this is the analysis followed by encoding scheme. So, what we have here, okay, that is to say speech followed by this bank of filters, it is a kind of analysis filtering, and then the speech extraction, which also is essential because speech forms an integral part of the analysis system. And for the proper synthesis of speech, what we have to do is to extract all these individual items, okay, out of the bit stream that is generated from the encoder. I mean, we are talking of what decoder is going to do. Decoder is going to extract all this channel information, pitch information, voiced, unvoiced flag, and then accordingly the pitch will excite the source, okay, and then accordingly we will be having the synthesis, that is to say this channel 1 to channel 19 outputs in turn will decide the spectral shape. So, this whole thing is called as the channel vocoder. The word vocoder basically originates from voice encoder. Okay. So, it is a very popular thing, and in this methodology is essentially what we have done here is a kind of parametric coding. And why parametric coding? Because we are not approximating the speech waveform like we do in the case of say pulse code modulation or the adaptive pulse code modulation and so on, which is essentially waveform approximating technique. But in this case it is completely parametric. We are not approximating the waveform, rather we are just making the analysis and then getting the information out of it. Now, in this process it is possible to represent the information in a much compact way as compared to the standard waveform approximating techniques. In fact, what one can do is that in Holmes channel vocoder, we require 48 bits to be encoded for every 20 millisecond. So, 48 bits to be encoded for every 20 milliseconds. Okay. So, that means to say that effectively the bit rate will be 2400 bits per second. Just try to compare this with the pulse code modulation technique, which I had told that is 64 kilobits per second. And why 64 kilobits per second? Because 3.4 kilohertz being the speech signal bandwidth, we decided to sample it at 8 kilohertz and represent 8 bits for each of the samples. So, that gives rise to 64 kilobits per second. As against that, we have got only 2400 bits per second. And again the reason for 20 milliseconds I think should be clear from my earlier lecture, that where I had mentioned that speech signal is essentially quasi stationary, and that quasi stationary behavior is assumed for a time between 20 milliseconds to 30 milliseconds. That is something quite typical. So, in 20 milliseconds of interval you can say that all these parameters that we are extracting, those parameters may be held constant during this 20 milliseconds of time. And what is the division of this 48 bits? Well, it goes like this, that we have 6 bits allocated to encode the pitch information. So, 6 bits are needed for the pitch information encoding, and it is in fact logarithmically encoded. So, pitch which is logarithmically encoded, that requires 6 bits of information. Then we require 1 bit to specify the excitation type, and what is that excitation type? It is the voiced unvoiced decision, and then we require 41 bits, okay, to encode the output of 19 filters, okay, 41 bits to encode the output of 19 filters. And how that is arranged? Actually 3 bits are there for encoding the absolute level of channel 1. Channel 1 means remember, channel 1 is the lowest frequency. So, its absolute level is encoded in 3 bits. Absolute level of what? Absolute level of the rectified and digitized signal. I mean, that is to say that essentially it represents that that what is the amplitude of the signal component that is present for the lowest frequency band. So, that requires 3 bits, and then from channel 2 onwards we do not encode the absolute level, rather we just encode the channel to channel difference. Okay. So, means when we are encoding channel number 2 will be the very next filter bank from the lowest frequency, and its output will be encoded, okay, using the channel to channel difference, and channel to channel difference requires less number of bits, whereas 3 bits are needed for absolute level. The channel to channel incremental difference needs only 2 bits. So, 2 bits for each channel to channel difference. And how many such channels are to be encoded? We have already encoded the channel number 1. So, that requires 3 bits, and then the remaining 18 channels, 2 bits for each channel to channel difference. So, what we have is 3 plus for 18 such channel to channel differences, we have 18 into 2. So, 36 plus 3 39, and we reserve 2 bits for signaling or monitoring. So, 2 bits are reserved for signaling. So, in all we have 3 plus this channel to channel 18 differences, which is 36 plus 2 bits for signaling, all total 3 plus 36 plus 2 41 bits. So, 41 bits for all the 19 filters, 1 bit for excitation, 6 bits for pitch. These things together makes it 48 bits. So, 48 bits we need to encode for every 20 millisecond of time, okay, requiring 2400 bits per second, which is pretty low. I mean, astonishingly low if you compare that with the regular PCM's bit rate. So, now having understood all this, we are in a position to talk about the main topic of today's lecture, which is actually speech coding. I mean, I will talk about some basic fundamentals of speech coding, and in this I will be talking about its objectives and requirements. Now, I have already told in the first lecture itself that the speech coders can be divided into 2 distinct classes. Okay. One is what I mentioned as the waveform approximating coders, and the other is the parametric coders. Examples you already know: waveform approximating coders, PCM, ADPCM, these are waveform approximating coders, and parametric coders, as I described just now, one form of parametric coder is the channel vocoder which I just now described, but there are other advanced parametric coders which have been developed till date, and many of these channel parametric coders are highly efficient and they are capable of producing a natural sound. Okay. And I mean it can produce something very close to the natural speech signals, and that is why it is very popular. Okay. Now, there is also a third class, okay, which we sometimes talk about, and that is called as hybrid coders. Okay. In fact, hybrid coders try to take the advantage of both these methods, that is waveform coding as well as parametric coding, and some of the examples of hybrid coders, very popular example is what is called as code excited linear prediction. Now, linear prediction is required for the parameters, because as I have already told you in my earlier lecture that essentially the vocal tract is modeled as a linear filter. So, you need to have some linear parameters, okay, which is based on the linear prediction. So, linear predictive coefficients are to be encoded, and then this is code excited, and in short form this is referred to as CELP or SELP. Okay. And also the multi-band excitation technique. Okay. We are not going into details of this right now, but later on we will be talking more about the parametric encoding scheme. Okay. So, multi-band excitation basically correspond to what we call as the MBE, in short form it is referred to as MBE. Now, just to tell you about some qualitative difference between these two major forms of coders, that is waveform approximating and parametric, okay, we can just give a subjective comparison in this manner. We just plot in the x axis, we indicate the bit rate, and the bit rate we indicate in units of kilobits per second. And what we do is that we choose a logarithmic scale to represent this. So, here here I wrote as 1 means that it is 1 kbps, and then we just keep dividing into regular intervals. This is 2, this is 4, this is 8, this is 16. So, you can understand that it is divided in logarithmic scale 32, 64, 128 and so on. Okay. More than that we do not require, because the at the high end we have up to 64 kilobits per second. Okay. That is for the pulse code modulation, as I have talked of. And here on the y axis we indicate the quality. Now, when we say quality, it is somewhat subjective. Okay. So, how do we assess the quality subjectively? Well, there what we do is that we just form kind of a mean opinion score. That is to say that if you ask a group of people to evaluate the performances of different coders, and if you ask all those listeners to make a choice that okay, on a scale of 4 or on a scale of 5, you just indicate that whether it's of excellent quality or whether it is good quality or fair quality, then then you collect all these responses, and using these responses you just form a statistics that that whether most of the people really liked this coder output, or whether this coder output is not being not being rated well by the listeners. So, like that you have some kind of a subjective assessment, and then you just have it as a scale of poor, poor is the lowest, fair, okay, then good, and at the highest level you can have it as excellent. Okay. So, definitely what we are trying to do is that we should definitely have, I mean we should definitely try to reach the excellent. The ideal situation would be that we should reach excellent quality at very low bit rate, but as you know that is not possible. In fact, the trade off goes in the other way. That means to say that as we decrease the bit rate, I mean if we go more on this side, decreasing the bit rate obviously requires sacrificing the quality. Okay. Basically there is loss of information. If you are going in for waveform approximation techniques, then the way by which you can achieve a lower bit rate is to use very coarse quantizations. So, coarse quantization means you are sacrificing the finer levels, okay. You are very crudely quantizing, and as a result of that your quality is going to suffer. So, definitely you can expect that a very low bit rate, the quality will be poor anyway. In fact, I mean going by this bit rate figure, for waveform approximating coder, one can just forget about having anything in the 1 kilobits per second, impossible. Okay. So, we have to try that out, the waveform approximating coders. Okay. After 4 or 8 kilobits per second, generally the quality becomes somewhat acceptable. So, if we draw a curve, okay, based on a number of listeners' observations, the listeners normally tend to have a rating something like this, that 2 kilohertz of 2 kilobits per second, they would definitely call the presentation to be poor, but when you go in for a higher bit rate, okay, then your quality improves. But beyond certain point, like here you can see that after 32 kilobits per second to 64 kilobits per second, the improvement may be just a bit of marginal improvement. Okay. But nobody is really rating it to be excellent, but something between good and excellent. Okay. If you want excellent, maybe you have to go in for a much higher bit rate, so that essentially, I mean unless you have absolutely lossless encoding, it is not possible to reach the excellent variety, because excellent category means that the original speech and the decoded and reconstructed pitch, they should be indistinguishable from each other. Okay. So, this is the curve that we should get for waveform approximating coders. And then for the parametric coders, actually what happens is, parametric coders, the one that I had described little while back. Okay. One thing that you are not exactly using things like quantizer, etc. So, there is no waveform approximation that you are trying out. You are going into the totally different domain, that you are making an analysis and then just subdividing into band representations, and those bands are quite a crude form. Even though you have 19 filter banks, but 19 filter banks representing a band of 3.4 kilohertz definitely means that, I mean you have some good amount of bunching, in the sense that, I mean a group of frequencies you are, I mean clubbing into one particular channel. So, obviously, you have loss of information, and the parameters that you are extracting, it is definitely not giving the kind of natural feeling, and as a result of that, the performance of parametric coders are generally much poorer as compared to the waveform approximating coders. So, something of this nature, a curve of this nature may be obtained. So, this is for parametric coders, but definitely by comparing these two curves, we can have a good inference, in the sense that just see that if you want a very low bit rate coder, okay, then realizing it using waveform approximating coders will not yield you a better result, because like say for example, you have it, you take it somewhere around 3 kilobits per second or so, you definitely find that the parametric encoders are better in performance as far as this curve is concerned. Only for higher bit rate, when you can have bit rate beyond 4 kilohertz, then definitely according to this curve we find that the waveform approximating coders, they perform better as compared to the parametric coders. Okay. Hybrids, okay, hybrids will fall somewhere in between this waveform approximating and the parametric coder class. Now, some of the basic objectives of speech encoding we need to understand, and that is to say that what is the quality and what is the quality requirements of this. Okay. So, there is, as I was telling you a little while back, that there is always a trade off between quality and capacity. Okay. You go in for a higher capacity channel, you can deliver a good quality speech output, and you compromise on the capacity, that is to say you go in for, if you are constrained to use a channel of lower bit rate capacity, then quality is definitely going to suffer. Now, this trade off is very easily understood, but the point is that there should be some regulatory bodies to monitor the quality, especially whenever you are working in the public domain, like the public switched telephone networks. Whenever you are in the public switched telephone network domain, okay, which in short form we all call as the PSTN. For PSTN, what should be the quality requirement for a given capacity, that must be fully specified, like that quality anyway we should reach, we have to reach. So, that is specified by some regulatory bodies, and regulatory bodies for, one international regulatory body that specifies for PSTN and other networking requirements, other channels, and that regulatory body is the International Telecommunication Union, or ITU. In older times, it was known as the Consultative Committee of International Telephones and Telegraphs, CCITT. So, all the old timers must have heard about CCITT standards, and now it is called as the ITU standard, the International Telecommunication Union. Of course, there are other regulatory bodies for specifying the GSM speech quality standards, or for the CDMA speech quality standards for the mobile phone applications. Now, so essentially what one has to do is that the speech coders that we design, okay, should be designed according to one such standard specified by the ITU, so that one follows the regulations very strictly. Okay. Of course, for absolutely private networks, like within one enterprise, or say for military systems, okay, they can afford to deviate from their ITU standards, but as long as you are in the public switch telephone network domain, you have to abide by the ITU. So, definitely the quality versus capacity compromise you have to do in accordance with the standards, and various standards have come up. We will very shortly talk about some of these standards. Okay. Another requirement that comes for the specification of the speech coding is the amount of coding delay. Now, coding delays essentially has got three components. Okay. The coding delays may be algorithmic. Essentially, the algorithmic coding delays that arise out of buffering of signal. You see, your algorithm may be requiring analysis of the past samples, and if you want to analyze the past samples, several past samples are to be used for the analysis, you have to have some kind of a buffering, okay, or you want to measure some statistics, okay, you have to store it for some time. So, the buffering is required. So, algorithmic coding delays are very much possible. The next thing is the coding delay that results from computations. So, those are referred to as computational coding delays. So, it means to say that essentially in a very I mean in a different language we can also call that as the processing delay. Actually, whenever we are using a very standard PCM, for example, there we hardly have any computation, because all that we are doing in a PCM is that we are taking sample by sample and then we are just approximating that sample, okay, using some quantization, and the quantized signal we are representing by bits, and it is that bits which we are sending in the bit stream, as simple as that. So, there is no computational aspect that is involved, whereas as you go in for more and more sophisticated codec designs, okay, there the computational design there the computational coding delays comes into picture. Okay. So, we will be seeing that if we have to encode the speech at a very low bit rate, okay, for which we have to use the parametric coders, okay, but to extract the parameters for that, to derive or to extract the linear predictor coefficients, okay, what we have to do is to do lot of computation and processing will be required within the computer. So, naturally more amount of processing gives rise to processing or computational delays. So, that becomes significant when you go in for lower bit rate codecs. Okay. And the third delay is of course due to the transmission. Now, this is certainly not within your control, because if you are doing long distance communication, then transmission delays are definitely inevitable, but what one can do that from the encoder itself, one should design the encoder in such a way that the algorithmic and the computational delays are minimized. In fact, we would be calling those speech encoders to be more efficient, okay, for which the algorithmic and computational delays are minimized to a great extent. In fact, what bad effect do we normally see when there are coding delays? What we have is that when coding delays occur, that time I mean the speaker is often irritated with a kind of echo that takes place. If there is a coding delay, then from the source to the destination, it ultimately gets played back at the destination at a later instant, okay, which may be something of the order of, let us say, 100 milliseconds or 200 milliseconds. If that happens, then there will be a round trip of that, because the speech signal what is produced at the receiving end, a part of that again comes back to you in the form of echo, and that echo is really interfering with your normal speech process. Okay. I do not know whether I mean it must be that some of you must have experienced this kind of echo effects. Okay. So, coding delays should be minimized for the reduction of the echoes. In fact, when you have something like a 64 kilobits per second PCM, then neither do you have any algorithmic delay nor do you have any computational delay. It is just the transmission delay that comes into effect, and normally with transmission delays we do not have that much of problem unless it is a very long route that it is taking. Otherwise, I mean this is perfectly fine, but algorithmic and computational delays are definitely something that needs to be minimized. And then while designing the speech coders, one should also take into consideration the channel and the background noise. And whatever encoders that we design, okay, should be adequately robust against these. So, channel and background noise robustness, that becomes a very important consideration. Okay. Now, typically the source coding of speech, okay, that requires only a fraction of the total channel capacity, because what we have to do is that in order to make it somewhat robust against errors, okay, we generally incorporate some forward error correction codes, okay, or what we call as the FEC. So, FEC requires a substantial fraction of the bit stream, like I mean if your actual data bit stream or the speech samples that takes this much, okay, your FEC may be taking this much. So, definitely since the error robustness requires lot of extra information to be sent in, it is tending to be somewhat inefficient. So, rather than having data or rather the source coding outputs as separate and then embedding the channel coding by providing the forward error corrections, okay, and having a complete scheme like that, it is better that if we have a combined channel and source coding, in the sense that at the time of source coding itself, if it is possible to specify that what should be the I mean during the source encoding itself, if we can take care of the robustness, okay, so that if a part of the data is lost, okay, if a packet is lost, then we should be able to recover the bit stream, okay, with minimum amount of perceptible loss. That is important, because for speech at least the perception is highly crucial, okay, whereas in the case of images, okay, it may not be that crucial, because some of the pixels may get disturbed, okay. You may not be able to view some pixels, okay, if it is affected by noise, or even if there is a loss of one single frame, you may not notice that, because if the very next frame onwards it is available correctly, then you will not even notice anything. Whereas, in the case of speech, if there is a discontinuity, then it really affects the intelligence aspect. That means to say that your understanding will be completely affected, your understanding of speech output will be affected if you have such kind of discontinuities. So, error robustness is very important, and more so from the consideration of today's technology of wireless communication, mobile communication, because the mobile communication is definitely subject to burst errors and packet losses are possible. So, one has to take care of the channel as well as background noise. Now, so far we were talking about the channel noise reduction. The same thing also applies for the background noise reduction, that whenever you have background noisy background environment, then your speech encoding should be able to extract the signal or maximize the signal and reduce the noise content at the source itself, and then you can have a better background noise reduction, robustness against background noise. So, these factors are all very important while designing the speech coders, and as I was telling you that a number of speech coding standards have been proposed in the recent years. Why recent? I should not say recent, I mean right since 1972, I mean the standards have come up. So, we will be just listing some of the standard speech codecs, okay, which have been adopted by the ITUT narrowband speech codecs. So, let us present a list of that. Now, we begin with the oldest speech codec. Okay. So, here we just list the name of the coder or the what you can say, I mean the standard number that is assigned, because every standard coder has got a type number that is associated with that. And then we also mention the corresponding bit rate for that coder, and then we also specify the delay we specify in milliseconds, okay. And then the kind of quality. Actually, what ITUT specifies is that it should be of a good quality, which they refer to as the toll quality transmission, okay. So, a toll quality requirements or at least a near toll quality requirements must be met. And then we also say that in which year was that standard adopted. So, we begin with the G.711 coder, okay, which is basically an adaptive and mu-law PCM. We will be coming very shortly, I mean in I suppose in the next 1 or 2 lectures we will be covering this adaptive and mu-law PCM. Essentially, as I had told you already, that PCM conforms to a bit rate of 64 kilobits per second. So, in today's technology 64 kilobits per second is definitely high, but okay, on the other hand, going by the coding delays and the quality, it is really very good, that its delay you can say almost as 0 milliseconds. I mean forget about the transmission delay, but as far as the coding or as far as the algorithmic and computational delays are concerned, it is 0. And the quality that this delivers is the toll quality, and this was actually proposed in the year, this was adopted in the year way back in 1972. So, 35 years back from today. The next encoder that we have is the G.726. In fact, G.726 it came much later, it came in 1990, and G.726 is based on the adaptive differential pulse code modulation, which we call as the ADPCM. We will of course be learning about the ADPCM with a great deal of details in the other lectures. Okay. In the lectures to follow, you will learn details about this, but just to suffice by telling you in a nutshell that here the bit rate that we have obviously is expected to be much lower than this 64 kilobits per second, because as I mentioned in the very first class, that differential way of representing the information reduces the dynamic range of the signal content, in the sense that we are making a kind of waveform approximation, right. So, we have the input speech, and then we have the speech that is predicted, the speech signal that is predicted, and which is based on the past samples, past speech samples, and then it is the error in the prediction what we encode, and that is a simple differential pulse code modulation, and we make the step size of differential pulse code modulation as adaptive, giving rise to ADPCM that caters to different bit rate requirements, and the bit rates which are specified by ITU-T, it caters for 40, 32, 24, 16 up to 16 kilobits per second. So, 16 if you compare with 64, definitely it is 1:4, a very substantial reduction. Now, ADPCM definitely requires some amount of buffering, definitely, because you see that how are you predicting the samples? You are predicting based on the past samples. So, obviously, you need to have some storage, okay, so that I mean as a result of that, it gives rise to delays which are of course marginal, because in terms of milliseconds it is just 0.25 milliseconds of delay, which is worse than this PCM, but somewhat better definitely, and the quality of that is also a toll quality. The next that we talk about is the G.728 encoder. G.728 is not exactly a waveform approximation coder, it is actually a hybrid coder which is LD-CELP. CELP stands for code excited linear prediction. I am not explaining this in detail right now. In fact, we will be talking about the CELP and the linear prediction in general, we will talk in the later lectures, and this caters for a bit rate of 16 kilobits per second, and the delay that is encountered in this process is somewhat more, 1.25 for toll quality speech, and this was proposed in 1992. And then came G.729, which is also another variety of the CELP, CSA CELP, and this brings down the bit rate to 8 kilobits per second. This was adopted in 1996, and this also gives toll quality, but in order to make it work at 8 kilobits per second, which is a substantial reduction in bit rate, 8 times as compared to the original PCM, but on the bad side of it, it incurs a delay of 25 milliseconds. Of course, I did not write milliseconds, because here all the delays that I am talking of is referred to in milliseconds. So, it is 25 milliseconds for that, and the standard G.723, okay, which was actually proposed in 1995, that gives rise to near toll quality, and on the bit rate side it comes to as low as 6.3 or even as low as 5.3, but delay is tremendous, it is 67.5 milliseconds, a substantial delay. So, you can see that as we are going in for more efficient bit rate coders, okay, the delay increases. And although till here we are able to maintain the toll quality, anything below 8 kilobits per second, you are no longer able to give the toll quality, but you have to give a near toll quality. Okay. And in fact, for the mobile standards, they have accepted the near toll quality. And for the GSM mobiles, okay, for the GSM, the standard that is adopted by the European Telecom Standard Institute, European Telecommunication Standard Institute, or what is popularly known as ETSI, ETSI. Okay. ETSI specifies a bit rate in the range of 5.6 kilobits per second to 13 kilobits per second. In fact, 13 kilobits per second is the one that you are getting as at full rate, and 5.6 kilobits per second what you are getting at half rate, and there the delay is of the order of 40 milliseconds. So, definitely we have to accept this higher delay, because for mobiles, I mean, even this 13 kbps of bit rate is on a very high side. For the CDMA, the standard that the North American standards which are existing, that is by the Telecom Industries Association, or Electronic Industries Association, in short form called as TIA or EIA. So, they had jointly formulated the standards TIA/EIA standard, that essentially specifies a bit rate of 0.8 kbps. So, it is really low at the lower end, up to 8.5 kilobits per second at the higher end, and the delay that we are talking of for the CDMAs, the code division multiple access, that is 45 milliseconds, considerably high both for GSM as well as for CDMA, and also for very low bit rate codecs what ITUT have proposed. So, in all, I mean, in a nutshell, what we learnt is that speech coding has got a few fundamental requirements, and the essential point is that whatever speech output that we produce, okay, must adhere to certain standards that has been I mean stipulated by ITUT, ETSI and other standard bodies. Okay. And we will be, I mean, in the next lectures we will go into the basics of the codec design. So, we will start with the waveform approximating coders, and we will understand that how the quantization is going to affect the quality, the quantization noise, the corresponding signal to noise ratio, and how we improve upon that. That will be our topic of discussions in the next few lectures. Thank you.